When you're asked to design a central heating installation, what the customer's looking for is comfort. So the first thing to decide is what we mean by comfort conditions. There are three factors which affect thermal comfort: room temperature, how often the air in a room is changed, and the humidity. The factors will alter according to which room you're dealing with. They'll also be affected by the level of activity in the room and how much clothing people wear there. The temperature needed in a bathroom, for example, is higher because there's less activity there, people are probably not wearing as much, and the air needs to be changed more frequently. In a bedroom, on the other hand, there's not much activity, but people are under duvets or blankets, and so the temperature can be lower and there are fewer air changes. So when we're designing a system, we have to think about these differences. First of all, we need to understand what heat is. It's energy, the total energy of the moving molecules in a substance. The faster the molecules move, the hotter the substance. And the more heat energy there is in an object, the higher its temperature. Temperature also depends on how big an object is and the material it's made of. Some materials warm up more easily than others. When designing heating installations, what we need to consider are the three ways in which heat is transferred: by conduction, convection, and radiation. Conduction is the process by which heat travels from molecule to molecule through a substance. If you hold a piece of copper in a flame, you'll soon feel the heat in your hand. Do the same thing with a piece of wood, and you'll feel no change for a very long time. That's because metals are much better conductor than wood. This thermal conductivity can be measured. In crude terms, what we do is take 1 cubic meter of a particular material and heat it. We note the temperature at the face we're heating and the temperature at the opposite face. The object is to take 1 second to achieve a 1 degree difference between these two temperatures. The amount of heat needed to do that is the material's thermal conductivity. Convection describes the movement of heat caused when hot liquids and gases expand and so become less dense and rise, while cooler ones become denser and fall. The air rising from a match is hot, but underneath it, it's cold. Heat flows with these air currents. The air in front of a radiator, for example, heats up, becomes less dense, rises, and is replaced by cooler, denser air, which then heats up in turn, and so on. Conduction and convection both need a material substance, a solid, liquid, or gas, to allow the heat to get from one place to another. The third form of transference doesn't. With radiation, heat is transferred from a warm object to a cooler one across a distance. It travels in straight lines, and heat energy isn't given out until it hits an object in its path. Some of it's then absorbed. In spite of their name, radiators emit most of their heat by convection, but they do also radiate heat. The proportion radiated can be increased by painting them darker and putting reflective material behind them. The reason we need to heat houses is obvious: for personal comfort and because the heat inside them is continually lost through their fabric and through the effects of ventilation, deliberate and accidental. So to decide how much heat you need to put into a building, you need to be able to calculate the amount it's losing. First of all, fabric loss. That means heat lost through walls, doors, the roof, and so on. This will depend on many different things: how the place has been built, the materials used, their thickness, and the difference in temperature between inside and outside. Construction methods and materials vary between different house styles, but more importantly, the area for potential heat loss can vary quite considerably. Look at the difference in roof, wall and window area between a big detached house, for example, and a small terraced cottage or a flat. Figures are available which give average outside temperatures. These have been used to produce a recommended external design temperature of -1 degree Celsius. Now what we need to know is how to calculate heat loss through a fabric. To do that, we need a factor that'll tell us how fast or slowly different types of building construction lose heat. This factor's called their thermal transmittance, or U value. U values have been calculated for specific types of constructions. You'll find them listed in the course manual. To get the rate of heat loss in watts, we multiply the U value by the area through which the heat is passing in square meters. Then we multiply that figure by the difference between the outside and inside temperatures in degrees Celsius. In this equation, A is the area, Ti is the interior temperature, and To the outside temperature. If, for example, we take a U value of 2 and an A value of 15 and a Ti minus To factor of 19, we get a rate of heat loss of 570 watts. The amount of heat lost through ventilation varies. Of course, we can't do without some ventilation, but we do need to know how much there is and what effect it's having. Heat loss this way is usually defined as the volume of ventilation air moving through the room each hour divided by the volume of the room itself. In other words, the number of air changes per hour. To calculate the figure, we multiply the volume of the room in cubic meters by the number of air changes per hour, then by the temperature difference between the inside and outside as before. And finally, we multiply that figure by a ventilation factor. There's no U value for ventilation, but the factor is 0.33 multiplied by the assumed air rate change. In this equation, V is the volume of the room, and N the number of air changes per hour. Therefore, if we have a room with a volume of 54 cubic meters and an air change rate of 2 per hour, when multiplied by the interior and exterior temperature difference of 20 and the ventilation factor of 0.33, we get a ventilation heat loss of 713 watts. Now that we know how much heat is being lost, we can begin to work out how much needs to be put back in. But if all we do is replace the amount lost exactly, it could take ages for the house or flat to reach its design temperatures from cold. So to cater for that, we've got to allow some additional capacity. Usually, adding about 10% to the calculated heat loss will do the trick. If the boiler's supplying hot water as well as space heating, we usually need to allow an additional 2 kilowatts for a standard hot water cylinder size. So, having taken all that into consideration, we can work on our installation design. There's a rule of thumb we can use to decide on which boilers and heat emitters to choose. First of all, take a particular room and add together the design fabric and ventilation losses. Then add the allowance for heating up. Now choose an emitter whose heat output is as close as possible to that figure, but certainly not smaller. Now do the same for all the other rooms and spaces, and add it all together to get the total heat emitter requirement. Remember to add an allowance for domestic hot water. Then choose a boiler with an output as close as possible to this. Again, make sure the output's not less than the figure you've worked out. The final topic to look at in this section is insulation. It's an obvious means of reducing heat loss. Newer properties tend to be designed with better standards of insulation, but older ones have some familiar problems. Lots of heat can be lost through the roof, It's a large area and should be insulated with one of the many materials available. Always make sure the layer is thick enough and also that there's no risk of fire and that it won't produce toxic fumes when it gets warm. If walls aren't insulated, up to 35% of heat can be lost through them. Cavity walls should be filled with an appropriate material. Floors can account for 15% of heat loss. Upstairs that doesn't matter because they let heat rise from below, but the ground floor may pose a problem. If it's a suspended timber floor, materials can be laid between its joists, just as they are in the roof spaces. If the floor's solid, however, it's more difficult and much more expensive. It can be covered with insulating material, which then has chipboard or some other flooring laid over it. But a barrier's needed to make sure that water vapor doesn't condense on the cold concrete. Gaps around doors and windows cause drafts, especially when they're on outside walls. All gaps like this should be draft-proofed. But be careful never to block ventilators, grills or any other fixtures which are purposely designed and located to allow air to flow through them. There's no doubt that double glazing does help to reduce heat losses and eliminate drafts. It also helps to counteract the downdraft effect caused by warm air being cooled by cold glass and falling down the wall under the window. Hot water cylinders should always be pre-insulated or lagged with close-fitting jackets. And where water could be liable to freezing, for example in any pipework not in the heated part of the dwelling or in the cold water system, the pipes and cistern should of course be insulated. Different dwellings are going to need different systems. We're all familiar with what's called a wet central heating system, but there are several types. In this one, the circulation of water from the header tank to the boiler and cylinder and back depends on gravity. But hot water's circulated around the radiators by using a pump. The cylinder has to be high enough above the boiler to be effective. This sort of system is inefficient and costly because domestic hot water's heated to the central heating system temperature, about 82 degrees Celsius, instead of to the more usual 60 degrees. But if we install a motorized zone valve here on the primary flow and wire it to a cylinder thermostat, we can set the cylinder thermostat to 60 and the valve will stop circulation when that temperature's reached. This arrangement's called a C-plan. Other systems don't rely on gravity, but use a pump to circulate hot water to the cylinder and radiators. This is the S-plan. It has two-port motorized zone valves, which are controlled by thermostats on the cylinder and in a room. The Y-plan uses one 3-port valve, which again is controlled by two thermostats. Because this valve is a flow-sharing type, the Y-plan's suited to smaller central heating systems. Another possibility is the combination system. This is one in which both central heating and domestic hot water are combined in the one boiler. That means there's no need for a separate cylinder and all the pipework that goes with it. In this system, when domestic hot water is needed, the mains water flows through a calorifier, gets heated by the water surrounding it, and is delivered to the open tap. There's one more aspect of these systems to remember. They can be either open or sealed. An open system's open to the atmosphere. A sealed one isn't. Here's a typical open system. Note that the pump's installed on the flow, past the open vent. This keeps most of the pipework under positive pressure and so reduces the possibility of airlocks, pump failure or corrosion. Instead of being open to atmospheric pressure, the sealed system has an expansion vessel with a safety valve. Also, instead of the normal tank, it has a pressure gauge. It's important for this system to have a high-limit thermostat fitted. Inside the expansion vessel, there's a membrane or diaphragm. On one side of it, there's the system's water. On the other, air or nitrogen. As the water's heated, it expands and compresses the air. So those are the basic elements which have to be considered when designing an installation. But with each individual dwelling, there are lots of things to think about. A large house like this, with several big rooms, will make different demands from a smaller house like this. And a small flat needs yet another approach. That's why we need to know about all the different systems. We need to be able to deal with different houses and different circumstances. For the large house, with its greater demands, the S plan might be the preferred option. The semi-detached, with its less extensive requirements, might be fitted with the Y plan. And the flat, where there's no room for a header tank, may need a sealed system, and because there might be fewer taps, it might be suitable for a combination boiler. But there are no hard and fast rules. The bigger houses might benefit in some circumstances from having sealed systems or combination boilers. It depends on space, the number of taps that may be used, the family's requirements and so on. It's important to assess each location on its individual merits. As well as choosing the appropriate system, we also need to decide on the pipe circuit. Again, there are several types. Here, there's a single loop of pipe. It's usually 22 millimeters in diameter with 15 millimeter tails to and from the radiators. It's easy to install, but there are obvious problems of balance because the first radiator on the loop will be hotter than the last one. This means having to fit larger radiators at the end of the circuit. Because of these problems, this type of system is no longer installed. In the two-pipe circuit, balancing is much easier. The same size of pipe is used, but this time there are two loops, one for flow, the other for return. One- and two-pipe circuits are usually called small bore because they use pipe diameters of 15, 22 and 28 millimeters. Microbore systems like this one can use 8, 10 or 12 millimeter pipes to connect to radiators. These connecting loops are individual circuits which lead from 22 or 28 millimeter manifolds on the main flow and return lines. Microbore's easy to install, but it may not be suitable everywhere. In hard water areas there could be scaling, and if the pipe's diameter is reduced to the radiator it's serving, the radiator won't reach its designed output. So the choice of pipe is important and depends on lots of factors. Your manual has guidelines on how to calculate your needs. There are more calculations to make before choosing the correct pump for the circuit. On most of them, you can set the speed to suit the circuit. Factors affecting your choice are the required flow rate and the index circuit. The index circuit is the one with the greatest frictional resistance. It could be the furthest radiator from the boiler, or it might be a larger radiator with a high flow rate. There are charts to help you make your decision. When you've designed and installed the system, it has to be commissioned. If there's a programmer, check that it's working properly. Then do the same for all the other controls. While the system's hot, check all the water connections. Then turn off gas, electricity and water and drain the system while it's still hot. Now set the controls to the levels the customer wants. Check that the pump's at the right setting, and finally, balance the radiator circuits. When you're satisfied that everything's okay, you can hand the system over to the householder. Make sure they know how to light it and shut it down, and that they understand all the controls.
Oh, there we go there. So that's, you know, set the thing.
Dry systems use warm air instead of hot water. Air's drawn from the house and blown through a heat exchanger. A fan then blows it on through ducts to registers or diffusers around the house. It warms a house up very quickly and maintains even, controllable temperatures. The size of the ductwork needed makes it difficult to fit into existing buildings, so you usually find it only in newer premises. There are many different types of heaters. The one you choose will depend on what output's needed, whether the flue system's room-sealed or open, and where it's going to be installed, in a room or a compartment. Models can either have traditional controls or what's known as mod airflow. Mod airflow uses electronics to improve comfort, performance and economy. The householder chooses when the system operates and sets a wall thermostat to the comfort level needed. The thermostat continuously tells the controls in the heater how much warm air is needed, and they automatically adjust the gas burner and the circulating fan accordingly. The fan can be installed above the heat exchanger so that the warm air is blown downwards and distributed from the bottom. Installing it below the heater delivers the air upwards. This might be a useful configuration in a basement, for example. And if the fan and heater are side by side, the warm air is delivered horizontally. There are different methods of distributing the air. This is a stub duct. It's the sort of system you'll find in small houses and flats heating just 2 or 3 rooms. This radial arrangement has ducts branching directly from the chamber that holds the warmed air, known as the plenum. The branches shouldn't be longer than 6 meters. With an extended plenum, the main duct is the same size throughout, and different sized ducts branch off it for the various rooms. When the warm air unit's at one end of the house, the arrangement is usually a stepped duct. As branches are taken off and therefore less air passes through the main duct, its cross-sectional area is reduced. If you have to extend ducting, there are some do's and don'ts to remember. Wherever possible, connect new ducts directly to the plenum. Connect new ducts to the sides, not the end of existing ducts. Don't fit a new branch directly opposite an old one. Design for as few bends as possible. And remember that square bends present greater air resistance. One final point about ducts. Just like water pipes, they should be insulated. The warm air's delivered to rooms via diffusers or registers. Depending on what sort of room it is, diffusers can be located in floors or ceilings. Registers are fitted in side walls. They've got distribution vanes to deflect the air flow so that it covers the whole room. They should be installed so that their closable blades are directing the air downwards. The size of diffusers and registers is obviously important. There are tables to help you decide what's appropriate for a particular location. Equally important is where they're located. The air needs to be distributed evenly. Sometimes this will mean fitting more than one register. The air that's displaced by the warm air as it's blown into the various spaces returns to the heater through grills like these, known as relief air openings. It returns from all heated rooms except the kitchen, bathroom, WC and shower. Just like warm air ducts and registers, return ducts and grills and relief openings need to be properly sized. Once again, there are tables to help you with your calculations. If the heating unit is located in a compartment, it's important to fit a sealed duct from the return air grill to the heater. If you don't, air could be drawn from the compartment and stop the flue working properly. When an installation's finished and checked, the main thing to do is balance it. That means using various guide figures to perform a series of calculations which allow you to balance the velocities at each register. Basically, it involves running the fan at maximum with the electricity on and the main burner off. Then partly close the balancing dampers of the registers nearest the heater and open those further away. Now it's a question of measuring the air velocity at each outlet, dividing that by a guide figure and working out the average for all the outlets measured. Once you've done that, a final multiplication will give you the balancing velocities you need for each register. You can now hand over the installation. Remember to explain to the user what needs to be done to operate and look after the system. Designing and installing these systems takes time, skill and experience. It's a complex process, but it's also logical. It just needs a bit of patience. Good luck.